All right, this is experiment 14, which is solubility product and the common ion effect. What we are calculating today is the KSP, or the solubility product for calcium hydroxide. We are going to do this in water, so I have three different saturated solutions. In the first one, I just added water and 0.1 grams of calcium hydroxide. And I stirred for 10 minutes. It will not all dissolve. It is on purpose a saturated calcium hydroxide solution. And I am filtering that with gravity. So I'm just pouring it in, and gravity is pulling it down. So this is a gravity filtration. All right, so this one is pure water, and then I'm going to filter it out. So all of the solid calcium hydroxide will remain in the filter paper. Now this one is a sodium hydroxide solution, and it is 0.03330 molar sodium hydroxide with 0.1 grams of calcium hydroxide. I made, again, a saturated solution. I stirred it for 10 minutes, and I'm filtering it. So all of the solid calcium hydroxide that did not dissolve is going to be collected in our filter paper. So to make a filter paper, you fold it in half, then you fold it in half again. And then you open it up, and you have your filter. And then you take your filter funnel, and then it sets right in the filter funnel. All right, and so our third solution is 0.06660 molar sodium hydroxide with 0.1 gram of calcium hydroxide. Again, it is a saturated solution. I can stir all day, all night for infinity, and it will not all dissolve. So it is a saturated solution. All right, and so I will filter that one as well. So you see that it is a milky white, but when it comes out, it is a clear, colorless solution. All right, and so now we're going to titrate this to get our concentration of OH minus. So to titrate it, we have our HCl from experiment 12. So we're going to use our HCl from experiment 12. The base that we're going to use is each one of these solutions. The directions say to add 10 mils of calcium hydroxide. And when you do that, you get a pink solution. Then you add your HCl until that pink solution is a clear and colorless solution. I am going to use a burette just to make sure that we do not pass up the end point. It is very difficult here. You want one drop where it's a color, and then it is no longer a color. Again, if you went past it, it still is a colorless solution. Versus the other titration where you have no color going to a light pink. If you added way too much of the base, it's going to be a dark pink. You would know that you went way too far. All right, so I prefer to have it as two liquids that are in a burette so that I can do a back titration if I did not see the color change from a pink to colorless in one drop. If I did, then I'm good. If not, I will have the opportunity to do a back titration. All right, so I will probably do this both ways. All right, so I'm going to get a pipette. All right, so here's a pipette. Another reason why we would use a burette. If you use a pipette, you don't have to use a pipette because I'm doing it. Pipettes are much more difficult, especially the antique pipettes. All right, so we are going to learn the technique of pipetting and then I'm going to use the burette, and you'll see why. A burette is much easier to use than a pipette. Pipette is very accurate. It's similar to a volumetric flask in where there is just one line. That is it. This is a 10 milliliter. I probably can't see it, but anyway, it is a 10 milliliter. It says that upside down, yes. All right, so not 0.1 milliliter. It's a 10 milliliter. And it says TD, all right, at 20 degrees Celsius. So we are at 20 degrees Celsius, and TD means to deliver. All right, so when you deliver, you will see that I am not going to push out the solution. The solution delivers exactly 10 mils. So I put the meniscus right at this mark, and then I go over to my flask for the titration, and it will deliver exactly 10 milliliters. This is an expensive piece of glassware. It will deliver exactly 10 milliliters of that solution. All right, so let's get my flask. All right, so our first solution is over here. Move the camera a bit. All right, so it is still filtering. And again, the flask does not have to be dry. It does have to be free of any acids or bases. It does not have to be dry. It can be distilled water wet. All right, because we're going to do a titration in distilled water. We checked it already. It is a neutral. It's not adding acid. It's not adding base. All right, but we need to get exactly 10 mils out of here. Let's see if we have filtered enough to get 10 mils out of here. All right. All right, so this is where it is difficult. So I sucked up way past the line. You probably can't see, but I'm way past the line. So I have a beaker here that I'm going to collect any remaining. And I have to let go. This is like a straw with your finger over it. It's not letting the liquid out. When I release the pressure of my thumb on the top, it is going to release some of the liquid. Ooh, and too much. All right. So I am, a tiny bit off. So it is just underneath it by a tad. All right, so we want to do this perfect, and so I'm going to suck up some more. And this is showing why nobody likes to do a pipette. It is very difficult to release slowly and get that right on the meniscus. So it does take some practice, and I am a little out of practice. I can't remember the last time I did one of these. Like I said, I am out of practice. To get that to fall at the exact rate that you want it to is difficult. At least I am proving my point here that we don't like to use these. We would prefer, okay, so I need to, it has to go down smooth. All right, I did it. Okay, so now it is right on the meniscus. It is a perfect 10 milliliters. And so I rinsed out my flask. Again, it can be wet with deionized water. All right, and then you deliver it, which means you let go and it will go in. Gravity takes it in, and when you are done at the bottom, you will tap off on the sides. All right, but there's still a little bit in the tip, but that has been accurately measured that when you fill it up to the mark and you release it by gravity, exactly 10.00 milliliters of your calcium hydroxide solution has been transferred to your Erlenmeyer flask. So now we're ready for the titration, but of course we need an indicator. So this is calcium hydroxide, it's a base. So when I add my phenolphthalein, you know what's going to happen. And now you'll see it happen. The 4 drops. Alright, so calcium hydroxide is of course a base, and phenolphthalein in a basic solution is going to be a dark red. Alright, so a very dark pink color. Alright, and so now we're ready for our titration. So we pipetted 10 mils of our filtered saturated calcium hydroxide into an Erlenmeyer flask. It says to add 10 mils of deionized water. So it certainly didn't matter that it was wet with deionized water because it even says to add more. Alright, and so there is the addition of 10 more mils of deionized water. Again, it doesn't matter how much deionized water you add. Our deionized water is perfectly neutral. All right, and now we're going to titrate with our HCl solution. So in our purette here, we have our HCl solution, and so we are ready to do our titration. This one is a lot more difficult, because with the other titration, I knew when it was getting closer. When the pink lingered for a long time, I knew I was getting close to the end. I am not going to have that luxury. 1 drop is going to go from, I mean, it'll get to be a lighter color, but it's not the same. All right, so we need our initial volume. Our initial volume is 0.48 milliliters, 0.48. All right, so now we are ready to add our HCl. And we want to add this very slowly. Not want to pass up the end point. I do not want to pipette that again. Okay. Yeah, I forgot about my magnetic stir. All right, fine. I'm still swirling it myself. Maybe the next titration. All right, we're looking for 1 drop to go from this dark pink into a light pink. Actually, we don't want it to be gone. We want it to be a faint pink. And then 1 drop will turn it to light pink. Well, to colorless is what we want. 1 drop to go from a light pink to a colorless solution. getting lighter. All right, so here's our light pink, and then one drop turned it to colorless. All right, so our volume. Final volume. Ten point 10.68. All right. Let's add our HCl, fill this back up. And safety glasses back on. All right, so the next one, we're going to use a burette. All right, so here is my second solution. My second solution, the concentration of the OH minus was 0.03330. Now, this is a burette. I want to have this to be accurate, and so I have to thrice rinse. Every time I change a solution in a burette, you have to thrice rinse that burette. One. Two. And three. So now we're ready to fill it up. Remove the air bubbles. All right. Get an initial reading. Our initial reading for this calcium hydroxide saturated solution is 2.59. All right, so now we're going to get our Erlenmeyer flask. And again, the Erlenmeyer flask can be wet with deionized water. Again, deionized water does not add any acid, does not add any base. It is neutral. All right, we're going to go from our 2.59, we want to go down to 12.59 or somewhere close to that. We are at 12.59. All right, and so we see that there was some phenolphthalein in here, which is fine, because that's what we're adding next is phenolphthalein. All right, and so we know it's basic. We knew it was going to be basic, and here is our solution that we're going to titrate again. All right, so now we are at 0.55. So 0.55 mils. And now we're going to add our HCl until it is colorless. Now we're really close. All right, so one drop changed it from a pink to a colorless solution, and our volume. $15.95. 15.95. All right, so now fill this back up. All right. All right, so the third solution, we're going to also put that in our burette, and we're going to add the 10 mils from the burette again. Again, we are changing a concentration, and so we take our 0.06660 molar NaOH, and we're going to thrice rinse it. So we put in a few mils, we get our beaker. All right, even though it is a base solution, it is a different concentration. All right, so we thrice rinse it to make sure that our concentration is exactly the same. If we mixed it, there was water in here or a different solution in here, we need to know exactly how much of this is being added, not diluted with the other solution, or if you rinsed it with water, it would be diluted with water. And so we thrice rinse it. Every time you change your solution in a burette, you thrice rinse it. And the last one. All right, now we have thrice rinsed our burette, and so we can fill it. Alright, and then we open it up to get rid of the air bubbles. Alright, this time I'm going to do it a little different. I'm going to start at 3.00. Get my volumetric flask, rinse it out with deionized water. Again, doesn't matter if it is wet with deionized water. Deionized water is neutral. All right, so we're going to go from 3 to 13. So I'm going to add this until it hits 13. All right, it is exactly on 13. So we added exactly 10.00 mils of our third solution. All right, it's a light pink because it has a little bit of phenolphthalein in there. And so we're going to add 4 drops. All right, so we have our 4 drops of phenolphthalein. Again, we're going to titrate it until it has no color. Put 10 mils of deionized water. We need to get our initial .08. We're starting at 0.08 milliliters. All right, and this is our third solution, which is the 0.06660 molar NaOH with calcium hydroxide. Getting a little bit lighter. It's getting closer to the end. There we go. So 1 drop, change it. All right, and we are at 22.12 mils. All right, so let's go to the calculations. I have them on the board. I will carry it over to the board. All right, so we are doing the KSP of our calcium hydroxide. And so the reaction for KSP, you always have a solid. In this case, it was the calcium hydroxide. And that is going to dissolve, ionize into calcium +2 and 2OH minus. All right, so anytime you're doing a KSP, it is a solid, one reactant that is a solid going to its ions. And this is for compounds that are insoluble. So you would never do a KSP for any sodium salt, potassium salt. Those are always soluble. Calcium hydroxide is slightly soluble. It is not completely soluble. All right, and so initial, we're going to go with 0 and 0. Anytime we have it in water, our first solution, we're going to go with 0 and 0. Technically, you have OH minus is 1 times 10 to the minus 7. In this case, we can ignore that for now. It is insignificant in the amount that we will get for this. And so we're just going to put 0. All right, and so the reaction has to go to the right regardless. We had deionized water has 0 calcium plus 2. So it goes to the right. When we do a KSP, we talk about the solubility. So instead of using the letter X, we use the letter S, which is its molar solubility. And so you have S for calcium, you have 2S for the OH minus because of the balanced reaction. There's 2 OH minuses. So at equilibrium, this is our ice over here, initial change equilibrium. We have S for our calcium plus 2. We have 2S for our OH minus. All right, so now we did a titration. So we had collected our OH minus, and then we did a titration with our HCl. For our titration, the net ionic for the titration, we did not titrate solid calcium hydroxide. We filtered it, and we only titrated our OH minus. So when you filter it, we just had OH minus. There was no solid. We filtered it. OH minus is all that went through, the aqueous OH minus. And we titrated that with HCl. The net ionic, HCl is a strong acid. And so you end up with H plus OH minus goes to H2O. So your titration equation is MV over C is equal to MV over C because you are using 10 mils of your OH minus solution and you are titrating with your HCl aqueous. And the coefficients right there, both 1s. So your coefficients are both 1s. So you get your molarity of your HCl from experiment 12. That goes for your H plus. The volume of your HCl, that's what you get from your titration. And then the molarity of OH minus, that's what we're solving for. The volume of the OH minus, we did 10 mils for each one. All right, and so you'd put in your 10 mils for that volume. Again, you have volumes on both sides. If you're going to use milliliters and milliliters, that's going to work. If you use liters and liters, that will work. All right, the only time you have to have liters is when there's a solid on one side. This is 2 liquids. All right, so your molarity of OH minus is equal to 2S. So you solve for molarity of OH minus, that is 2S. Then you divide both sides by 2, and you have your S value. And so once you have S, you see that S is your calcium hydroxide or calcium plus 2 ion. Your 2S is your OH minus. And to calculate your KSP, the KSP is always for calcium hydroxide, the concentration of calcium plus 2 times the concentration of OH minus squared. So you plug in your numbers and you get your KSP. All right, so this was a KSP. It was also a common ion effect. So in solution 2, we did exactly the same thing, except in solution 2, we added 0.03330 molar NaOH. So instead of water, we are in 0.03330 molar OH minus. All right, and so again, we're doing ice, but our calcium plus 2 is 0. We didn't add any calcium. But our OH minus concentration initial is 0.03330. The reaction has to go to the right because calcium plus 2 is 0. And so you have plus S, you have plus 2S because there's 2 OH minuses. So at equilibrium, calcium plus 2 is S. Your OH minus is 0.03330 plus 2S. All right, and then we did a titration. So again, the titration is of the 2 liquids. The HCl is titrating the OH minus solution that we filtered. So again, MV over C is equal to MV over C, exactly the same as we did the last one. All right, so it's your molarity of your HCl from experiment 12, volume of HCl, what we used in our titration. The coefficients, again, are both 1s from our balanced reaction there. H plus and OH minus give H2O. Molarity of OH minus, that's what we're solving for. The volume of OH minus, again, we use 10 mils all 3 times. All right, and so your molarity of your OH minus is 0.0333, I'm missing a 3, 0, let me fix that. One more time. All right, so it is 0.03330 plus 2s. All right, and you're calculating the molarity of your OH minus from the titration equation. And so to solve for S, you have to subtract 0.03330 from both sides, and then you have to divide both sides by 2. All right, and so once you get your calculation done and you know your molarity of OH minus, you subtract 0.03330, then you divide that by 2, and that will give you S. All right, and so S is your calcium plus 2 concentration. Your OH minus concentration, you know what that is because you got that from your titration. And so you will put your calcium plus 2 concentration and your OH minus and square it, and you will get KSP. Theoretically, the KSP is a constant, so you should get the same value for KSP from doing this in water as you would in putting this in base. Now, the common ion effect, along with Le Chatelier's principle, when you add product, the reaction's equilibrium shifts to the left. All right, but it can't go left because you have a 0, which means less is going to go to the right. So your solubility should decrease anytime you add product. So in the third one, we even added more of our OH minus. We used 0.06660 molar OH minus. And so the amount coming to the right should be even less, which means our S value should be even lower. Again, the KSP should be a constant. That is an equilibrium constant, and it should be the same for all 3. It is experiment. There's going to be some experimental error, but theoretically they should all be the same. All right, and so again, you have your titration equation, MV over C is equal to MV over C. Again, you have the molarity of your HCl from experiment 12, volume of HCl from our titration. Both coefficients are 1. Molarity of OH minus, that's what we're solving for. Volume of OH minus, 10 mils every time. All right, and so once you get your molarity of OH minus, that is equal to 0.06660 plus 2s. To solve for S, you subtract both sides, 0.06660, and divide both sides by 2, and you will have your S, your molar solubility S. Again, when you put that in, for your S is always your calcium plus 2. You put that in for your calcium plus 2. You put your OH minus concentration and square it, and then you have your KSP. Again, theoretically, the KSPs should be the same. Solubilities should get lower as you added more of your product. And that is it for experiment 14.